Now we will start the next chapter, that is the last chapter of this book, that is forced oscillator. That is forced oscillator. You know that the word force means an external periodic force is applied on the oscillator to produce the oscillations, which is called forced oscillations. So, what is this oscillator? It is an oscillator which produces oscillations under the external periodic force, under the effect of external periodic force. So, we will discuss two types of forced oscillators. First one, forced mechanical oscillator. And second one is forced electrical oscillator. So, what is mechanical and electrical? These are oscillators which we have already discussed in the previous chapters. Mechanical means spring mass. Electrical means LC circuit. But when we apply an external force, that force must be periodic. So, that force which is applied on the oscillator should be periodic force, periodic or external force, and this force is mostly in the form of F naught e raised to power iota omega t, e power iota omega t. Iota omega t means e power iota omega t means cos theta plus iota sin theta, that is cos omega t plus iota sin omega t. So, both cos and sin functions are periodic functions, and hence it is called periodic force. So, this force is applied on the oscillator after a fixed interval of time, that is after a fixed time period. So, we will discuss these oscillators one by one. So, first of all, I will discuss forced mechanical oscillator. So, it is nothing simple. A spring is attached with mass, or mass is attached with spring, that is SM problem. Both are lying here on the table. This is a table. So, when we apply force on it, this is deforming force, and in the spring there will be a restoring force. So, F1 deforming, F2 restoring, and the frictional force or damping force is F3, and another external periodic force F naught e power iota omega t. This force is also applied on this oscillator to produce oscillations or forced oscillations. So, in this case, the equation we will draw the equation of motion for force oscillator. So, we will derive equation of motion. So, what is equation of motion? It is nothing, it is the equation of force, means we will compare different forces and make an equation. That equation is called equation of motion. So, you know that in damped oscillator, the equation is, in damped oscillator, the equation is force is equal to ma, because you know that there are four forces. F1 is ma, F1 force ma, that is m into d square x upon dt square. F2 is minus r dx by dt, and spring force, third force, is minus Sx. So, this is deforming force, this is force due to spring, that is restoring force, and that is damping force. But in case of force oscillator, another force, that is fourth force, is also applicable, e power iota omega t. So there are four forces which are acting on the system. You know that in our first chapter we have made the equation by two forces, that is first deforming and this third one is restoring, by these two forces. In damped force there are three forces, F1, F2, F3. Now in force oscillator there are four forces. So one more force is added in the subsequent manner. Now the equation for this force oscillator will be, first of all we will prepare the equation by these three forces, that is m into d square x1 dt square is equal to this one minus r dx by dt and minus s into x. These are deforming force, these are restoring forces or negative forces. And on taking these two terms on the left hand side, we will get m d square x1 dt square plus r dx by dt plus sx equal to 0. So this equation is equation of damped oscillator. Now the additional force, this force is applicable or applied on this equation, and finally the equation for force oscillator, equation of force oscillator will become m d square x1 dt square plus r dx by dt plus sx is equal to this force f naught e power iota omega t. So in this way the equation of force oscillator is formed. So this is the equation, left hand side is the same as that of equation of damped oscillator, and on the right hand side I have put this periodic external force which will be applied on this system but periodically. This force is not acting continuously, it will be periodic, means we will apply this force first of all, then we will release it, and after some time again we will apply this force and then release it, again after fixed time we will apply this force and release it. So this is periodic force. So this equation is called equation of force oscillator or forced mechanical oscillator. Now we will find the solution of this equation, as we have already familiar with this solution in previous cases. So what are the solutions of equation of force oscillator? Solution for equation of this force oscillator. So we will solve this equation. So this equation is very complicated because it is second order differential equation with iota is also there, complex number is also there. So the solution of this equation will be very complex because iota is already involved in this equation. So to find the solution, we will separate this equation in two parts, or there are two solutions, or we can say that there are two possible solutions. First one is transient solution or transient behavior, and second one is steady state behavior. Steady state behavior. So we will observe the behavior of this force oscillator in two different ways. First one is transient and second one is steady state. So what is transient? Transient is that behavior when there is no applied force, means initially this force is not applicable on the system. After a fixed time we will apply this force. So in the initial period this force is not there. Therefore the behavior of this equation is said to be transient behavior. That is, in transient behavior this force is 0, means external force is 0, and in steady state external force is not equal to 0. So, first one we will solve the transient behavior, that is transient behavior. So, in this case external force is 0. So, the equation will become m into d square x upon dt square plus r dx by dt plus sx is equal to 0, this one. If right hand side become 0, means the external force is not applied on it. So, this equation is same as, it is nothing, this equation is same as equation of damped oscillator, same as damped oscillator, because it is damped equation for damped oscillator. And you know the solution of this equation. There are three cases, that is heavily damping omega square is greater than b square, and critical damping when omega square is equal to b square, and third one is lightly damping when omega square is less than b square. So, there are three cases, we are already familiar with these three cases. Our transient behavior is same as the behavior of damped oscillator. So, we will not discuss this oscillator, this behavior in detail, because we are already proved it. So, you know that in three cases it is non-harmonic, but in third one the lightly damping is always harmonic behavior, means this type of behavior, harmonic, which is decreasing with the periodic function or harmonic function. And the frequency of this equation is omega dash is equal to omega square minus b square, or s by m minus r square by 4m square under root. This is omega dash. This is angular frequency of damped harmonic oscillator or lightly damped case. When harmonicity is there, it means in the first and second case there is no harmonicity. The harmonic function is only possible for the third case, that is we will discuss lightly damped case. This is the frequency of damped oscillator. So, this is transient behavior, which is same as the damped behavior or damped oscillator. And second one, steady state behavior. So, in this behavior, second one is steady state behavior. So, in this case external periodic force is not equal to 0, means external periodic force is also applicable. So, the equation is m d square x upon dt square plus r dx by dt plus sx is equal to f naught e raised to power iota omega t. So, this is the equation for steady state behavior, and we will solve this equation in detail and find out the different possibilities from this equation. So, we will discuss this behavior in our next lecture. Thank you very much.